Okay, great. So Demis, why don't you introduce this session and then we'll get started with Crystal's talk.
All right, so welcome back, everyone, or for those of you that were in the other sessions, welcome. The next series of presenters are going to be students that participated in NASA internships, which is one of the programs we have through the Minnesota Space Grant. So without further ado, so we get to listen from all the students and get to ask questions, let me introduce our first speaker, and that's going to be Crystal Compton from the University of Minnesota, Twin Cities. And Crystal, let's see.
I'm here. Am I able to share my screen?
I'm trying to give you access, and for some reason, it's not allowing me to do that.
Oh, you should be able to, Crystal. Have you tried?
Yeah, here, let me try. Got it.
There it goes. All right.
That's fine.
Okay, great. Well, thank you for the introduction. I am going to be talking today about some of my work with textile-based wearable sensors for body spacesuit assessment. And as mentioned, this was part of a summer internship that I had last summer with NASA Johnson Space Center. Specifically, I was working with the anthropometry and biomechanics facility there. And this is part of my PhD dissertation work as well. And is still currently in progress. So just a little bit about me briefly. So I am a PhD candidate currently at the University of Minnesota Twin Cities campus. So my work is very interdisciplinary, but broadly speaking, I study wearable technology, functional clothing design, and human factors and ergonomics. So I have worked in a lot of this work has been with the Wearable Technology Laboratory. And recently I've joined the Applied Sustainable Product Innovation and Resilient Engineering Lab with the Duluth campus. I have also, over my graduate studies, been an instructor for various textile, soft goods, and apparel assembly courses. And then I've been really fortunate to have a lot of different NASA experience. A few summers ago, I was also with the Advanced Pressure Garment Technology Development Team. And then I also was able to participate in the Reduced Gravity Education Flight Program. And I've also presented at different wearable technology symposium years at JSC as well. All of this is with Johnson Space Center. I also have interned with Microsoft, and then I was a product development engineer at Tactile Medical, which is a local medical device company over the years as well. So just a brief outline for my project. I'm going to talk about the intro and objectives and a little bit about the background first, and then some sensor and suit component development that I've done, and then briefly some preliminary sensor analysis that I've worked through. And also I'm going to cover current in progress work. As I mentioned, this work is still in progress, and then conclusions and future work. So spacesuit fit is obviously recognized to be a really important factor for crew member safety and performance. So achieving optimal suit fit is important to reduce negative aspects of working in the spacesuit environment. So this can include things like discomfort, increased energy expenditure, reduced mobility, and risk of injury. So one way to do this is by improving the understanding of the body-spacesuit relationship, which can provide important implications for suit sizing and fit. So the human body is a complex system and is used as the foundation for wearable product development. So as I'm sure everybody is kind of aware of, bodies vary greatly in sizes and shapes, which introduces challenges in the development of a sizing system to achieve optimal fit for your given target population that you're designing a system for. So with spacesuits, there are various things that you need to consider when you're assessing fit as well. So the suit needs to fit statically. So this also includes like dynamic poses, but then it also needs to fit dynamically. So it needs to fit while the body is moving. You also have to consider a lack of gravity as well and how that may impact fit. And fit testing must be performed to reduce various negative aspects related to suboptimal suit fit. And objective testing can inform the design of suits. So some motivation for this, spacesuits are kind of an example of a protective exoskeleton and functional wearable system where optimal suit fit is imperative for user comfort, but also performance as well. So the suit has or needs to fulfill a complex set of user requirements. And it also needs to provide protection and safety and health for the astronauts. And the suit also needs to provide mobility and remain functional for the human inside. You can't necessarily just put the human inside of a big bubble. It needs to remain mobile and functional. The human needs to perform various tasks and be able to work within the suit. So the Exploration Extravehicular Mobility Unit, also known as the Xcmu, is pictured here. This is the current suit that's in development for future Artemis missions, which focuses on planetary and surface exploration, which is a little different from previous suits and missions. So there are kind of two key aspects that this suit is aiming to improve. So first is increasing lower body mobility and range of motion, again, for that surface exploration, but then also accommodate a growing astronaut population with inclusive sizing, particularly focusing on like smaller female individuals. So understanding the human spacesuit interactions is imperative to improve the suit fit. So force, pressure, and contact sensing affords objectively evaluating fit by quantifying body wearable system interactions. And there are commercial systems that do exist, but they, through various NASA and other studies, they have not been effective for on-body sensing. So textile-based sensors preserve both wearability and comfort for on-body sensing. A soft connection is able to be made with textile-based sensors. And the disparity between kind of more hard or rigid electronics and soft textiles is a common failure point that's been experienced with trying to integrate traditional, like I said, hard electronics into clothing. With textiles, they can be easily integrated into clothing because, again, it's that soft-to-soft connection. It affords proximity to the body surface. It's also an existing layer that humans normally are already wearing, so it already is there. It also is a very thin form factor. So force sensing can provide kind of detailed information, but it comes with many challenges and potential contaminating variables for on-body and garment integrated sensing. So you have different things like sensing garment and body movement with these sensors and sensor deformation versus actual sensing of, say, like external forces being placed on the sensor. So those are different contaminating variables that can be challenging for force sensing. So contact sensing is a more straightforward, elegant, and easy to implement approach that can quantify body wearable system interactions while reducing these contaminating variables. So the project objective here is to develop and evaluate garment integrated textile-based wearable sensors to quantify body spacesuit interactions during dynamic EVA-like movements. So I am focusing for this project as an initial proof of concept on the lower torso assembly brief suit component, which is highlighted here. And this is going to be used for human in the loop testing. And it's used with this suit component as the LTA is currently in an active development and testing phase. And it'll be really useful to understand implications of lower body suit fit for planetary exploration. So part of my project was doing an extensive literature review. I won't go into details of this, but I performed a literature review to identify methods of assessing the relationship or interaction between the body and a wearable system generally. So I looked at things like spacesuit clothing and fit, how those are traditionally assessed, 3D body scanning and modeling, motion capture system, photography and video recording, suit symptoms and injuries, subjective feedback, and then my focus is on wearable sensors and filling that gap with textile-based sensors. So the aim here for this textile-based contact sensing is to quantify contact of the lower torso assembly brief suit component to inform various things, such as suit sizing and fit development, suit selection. So there are different sizes of components that the suit can fit. So it can inform suit selection for a given anthropometry or a body size and shape. Also, where to put padding on the user to protect against the suit, so padding locations, and then compare this information with subjective fit data, because subjective fit data can be sometimes kind of hard to understand what exactly it means. And then I'm going to be using this to compare with force and contact sensing to understand how also these force sensors how reliable they are, and using that with a triangulation approach with motion capture system to track the physical space of the brief and the body. So I'm using a robotic mannequin for sensor validation because it performs a sequence of cyclic gait cycles, and it's very repeatable. And so I can kind of capture what is happening with those sensors in that system. So then I have the sensor garment system kind of development, and there's multiple stages of that, and I'll kind of go over that in a few slides. First, you need the garment based development, then the sensor development itself, the sensor garment integration, lead materials and routing, which is a huge challenge for wearable on-body sensing, and then sensor and garment characterization. So listed here are just some validation and reference measures that I've kind of explored through this project. So this includes controlled force testing using an Instron tensile testing machine, optical motion capture system, and as I mentioned, force sensors, 3D modeling, and 3D scanning. So like I said, I'm using a robotic mannequin for sensor validation. And I took various 3D body scans of this mannequin to help with the virtual fit development and assessment of the brief suit component. So as I mentioned, the mannequin performs like a cyclic sequence of gait poses. So I aligned I cut the gait into different sections, and I took a body scan of the mannequin to then be able to do a 3D virtual fit assessment with the brief. So I had to develop a brief suit component that would accommodate this mannequin. And there were many challenges with that. I won't go into details of it, but I needed it to fit with this mannequin. And so I did a virtual fit assessment here, as you can see, and it was really super helpful because I ended up 3D printing the brief and it fit the very first time, which I'm really proud of. So it fits both statically and dynamically. One of the challenges with this is there's a metal bar on the right side of the mannequin that I needed to design around. So I needed to make the suit the component into two different parts to then and then have different parts to align them together and stay intact. And then I also, the brief needed to fit both statically and dynamically. The mannequin has a very large gait cycle, so that was a bit of a concern, and I didn't want to break the mannequin. So I'm really happy that it was able to fit. I did a little mini 3D print first, and then I moved forward with the final print, which was a success. I've also done a little bit with mannequin landmarking and 3D modeling to be able to virtually assess the mannequin movement with the brief movement, and that is still some work that's currently in progress. So then moving more onto the garment development, first the garment base pattern needed to be developed. So I needed to understand the user's anthropometry. Also, I needed to look into various material selection. So I needed to have a material that would accommodate this body movement and be able to stretch with the body, but also recover well. Then you have the pattern making process, which there's multiple steps that go into that with foundations and slopers that need to be developed, and it needs to be graded into different stretch categories based on the material properties. and the stretch direction. I did multiple fit test prototypes, including both physical and virtual, as you can see here. And there are some tension and distant maps that I used to aid in the development of this. And then some garment features. I needed to have some garment anchoring so that, or to minimize garment shifting or drifting during movement. So I used silicone backed elastic waistband and hem, and then stirrups to kind of anchor the garment on the body. So then here are just some pictures of the garment development initially. I also, now moving on to the sensor development and fabrication, I spent a lot of time working with different materials to kind of understand the different properties of using different materials on these sensors. So I tested different knits, wovens, and non-woven fabrics, different conductive textiles, non-conductive textiles, and adhesives, and then the size and shape of the sensor layers, which includes the lead attachment, interaction with other layers, and then kind of this garment integration and protective border. So there are a lot of different like intertwined variables that I was working through and challenges that I needed to consider. So pictured here are just some initial sensor placement. I wanted to have a sensor placement that would detect both areas of contact, but also areas of non-contact. So then I had the sensor garment integration. The integration needs to remain durable enough to be within the spacesuit environment, because after I do this testing, I'll be bringing my sensor system to NASA this summer for them to do full suit testing and then move on to possibly testing in the NBL with this. So I've explored different things like stitching, adhesives, sensor borders, and orientation and placement of it on the garment. So leads are a huge issue with on-body sensing. I've explored various options with this. It needs to, there needs to be enough space on the garment, and it also needs to not restrict body movement. So it needs to be extensible. And it also needs to not interfere with the sensors. So this was a big challenge that I had to work through. And I ended up using a serpentine pattern and kind of mechanically attaching it to a wire with a hand sewing needle to the sensors. And I kind of
give you a 1 minute warning if kind of, all right.
Thanks. So I tried to align my sensors with the lines of non-extension, which are essentially lines that do not deform on the body and kind of preserve mobility. So I've done some Instron testing with these sensors to understand their performance. Here's just some rough preliminary sensor data that I was working through, and then a sensor analysis method to determine the contact threshold. So some current in progress work is the controlled force testing with my final sensors, and then the robotic mannequin sensor validation with the motion capture system, human body shape assessment testing, and then I have a publication that's currently in works for this, and then my final PhD dissertation defense. So in conclusion, this method is helpful for NASA to improve understanding of wearable system fit and to be used in the suit development and suit padding selection. I kind of mentioned full suit testing after this and exploring different sensor fabrication approaches in the future will be helpful. I just wanted to say thank you to all the people who have helped make this possible along the way. The ABF facility, NASA intern program coordinators, University of Minnesota and my committee members, and the Minnesota Space Grant for helping support this. And that is it.
Thank you, Crystal. I think we're running a little bit behind on schedule, so if folks have questions, please contact Crystal. I got a bunch of them, so you're probably going to hear from me. Very interesting talk. Very interesting talk. Thanks.
Thank you. Yeah.
Demos, I think we have time. I think we should have time for at least one question, and I want to pose it myself. You've been to Johnson, but you didn't get to go last summer. Any comment about how was this experience as a virtual internship?
Yeah, it's interesting. I actually I had all of this planned originally, all of this had to be down there physically, and then I had to kind of sort of last minute like change everything. So I really had to like change my plans. It's still been super helpful to work with my team down there. But it is, you know, it is a little bit challenging being in a virtual environment, but I still had such a wonderful experience, and it's been really great to be working with my team virtually. And we've developed different methods to kind of make that work. So yeah, it's been overall really great.
That's great. So let me just stop this recording and start the next one, and then Demos, you can introduce the next speaker.
All right.